All right. Our first speaker for the day is Calabi-Yau from CalTech, and he's going to tell us about the Moduli space of Non-Archimedean Holomorphic.
Thank you very much for the introduction, and thank the organizers for the invitation. It's my great pleasure to come to Miami at the annual conference and speak here. The title of my talk is Moduli Space of Non-Archimedean Holomorphic Disks. It's work in progress with Keel. Here is the plan of my talk. So I'll begin. I don't know if you can see the laser.
Start from the wall. And
yeah. Here is the plan of my talk. So I'll begin with motivations and setup. Then I will give two trivial examples. After that, we will introduce the boundary regularity condition motivated by the trivial examples. And I will discuss formal models, reduction of germs, and the boundarylessness of the moduli space. And after that, I will introduce an alternative boundary condition and use this alternative condition to show compactness of the boundary of the moduli space. Then I will discuss properness as well as the bubbling, which is always a problem to take into account when we study this kind of curve counts. And by the end, I will talk about non-Archimedean deformation theory and the smoothness of the moduli space. So the whole talk is about moduli space of this holomorphic business, and we will be studying the various properties, boundarylessness, compactness, properness, and smoothness of the moduli space. Okay. Yeah. So let me start with the motivations and the setup. The motivations come from the SYD mirror construction of log Calabi-Yau varieties. Here is our setup. We have a U, an affine log Calabi-Yau variety over complex numbers, and our theory is algebraic essentially. So we can work over any field K of characteristics 0, and then we fix an SNC complexification Y of U, and we denote by D the divisor at infinity. So by log Calabi-Yau, here we mean that U has a unique volume form with at worst simple poles along the boundary divisor D. And we denote by I don't know if you can see the pointer. It's not so easy for me to see. If you can see it, then can you see it? Yeah. Then maybe I will not use it. If half of the people can't see it. Okay. Yeah. So the setup is very simple. We have a log Calabi-Yau variety, a fine log Calabi-Yau with some SNC complexification. And the log Calabi-Yau means that U has a unique volume form with at worst the simple poles, and the polar locus, the place where the volume form has poles, we denote by B essential. And for the purpose of mirror symmetry, we also assume that this log Calabi-Yau has maximal boundary, which is parallel to the maximal degeneration condition for compact Calabi-Yaus. So we assume maximal boundary, which means that this B essential contains a 0 structure. Okay, so let me give the basic example. If we start with YD, any Porta variety, and take U to be the complement of D, so U is just algebraic torus, then this is like the most basic example of log Calabi-Yau, just the complex, the algebraic torus, and the SNC complexification is given by the torus complexification. Now, if we follow up anything with center in the boundary, and we take y tilde to be the follow up, and the d tilde to be the strict transform of d, and the u tilde to be the complement of d tilde, then this is another. This gives other examples for this log Calabi-Yau with complexification. But we in dimension 2, one can show that essentially this is all the examples in higher dimension. Not all of Calabi-Yau have such toric model. Now let me introduce the non-Archimedean SYZ vibration for this log Calabi-Yau. In order to bring non-Archimedean geometry into our story, we equip our base field K with the trivial absolute value. So the trivial absolute value is takes values in just 0 and 1. The absolute value of all non-zero elements is 1, and the absolute value of 0 is 0. We can do it for any field. Yeah. Okay. So yeah. So we equip our base field K with the trivial absolute value. And now the base field K is a non-Archimedean field, and we can take identification. Non-Archimedean identification, and we obtain a K-analytic space. So this space is, in this case, it's not so hard to describe. As a set, it consists of pairs Casi-mu, where Casi is a steam theoretic point, and mu is an absolute value on the residual field of Casi. So here we see that the non-Archimedean identification is kind of some enhancement of the scheme, where for every scheme point, we also add all the possible variations of the residual field. That's all. But this construction actually makes the space into a pretty nice topological space that is locally compact and locally path connected. Oh, that's a very good question. So here I put the trivial absolute value because if we start, I want to eventually we are using non-Archimedean geometry just as a tool to study log Calabi-Yau variety. So what we start with is like a log Calabi-Yau variety over complex numbers. Then if I want to do non-Archimedean geometry, the only canonical non-Archimedean absolute value I can give is this trivial one. So that's why we are giving the trivial one. But it's a very good question. What about the non-trivial absolute value? So actually, it will just come naturally, the non-trivial one, because in the moduli space, we know that we have all the field extensions in the moduli space. Just as in algebraic geometry, when you consider a moduli space, then points in the moduli space, it's already defined over some bigger field. So automatically here, when we consider moduli space, then we will have a non-trivial variation. Yeah. So and also remember that we started with log Calabi-Yau. We have a volume form, and now we are in analytic geometry, so we can take norms of everything, and we have volume form. We just take a norm of volume form. This norm has a special name called the Temkin scalar seminorm. If we take its norm, we obtain an upper semi-continuous function. So you know in complex geometry, when we have volume form, and if we have some formation metric or some norm, we get a continuous function. Here in non-Archimedean geometry, we get something a little bit less. It's only upper semi-continuous, but that's not too bad. That's already good enough for our purposes. So it's upper semi-continuous, and we can take the maximum locus of this upper semi-continuous function, and this gives the so-called essential scaling of U. Yeah, maybe I should mention that the essential skeleton was first suggested by Conception and Sohoman in using SNC models, and by looking at the locus where the volume form has the poles. Here, this definition is due to Temkin, and we don't use any models. It's purely academic. And it's also more general, this definition of essential skeleton. It works over any non-Archimedean field, and it also works for any non-Archimedean space which may not have models. Okay. Yeah. So as I said, it was proposed by Conception Sohoman, and then later clarified by Smoothness and Temkin gave this more general definition. And they also proved that this theory is essential skeleton defined as the maximal locus of some upper semi-continuous norm of the volume form has actually a very complete geometric description. So it's homomorphic to the dual intersection cone complex for the essential divisor. So you remember we have essential divisor, and we take the dual cone complex of the divisor, and that is a complete geometric description of this essential skeleton. Okay. Yeah. So now we have this very complete geometric description. We ask what does this look like? What does this cone complex look like? For this, actually, it's already studied by the next Porta because it's essentially a question of directional geometry. So, assuming the minimal model program, we can deduce the following properties of this dual cone complex. In other words, of this essential skeleton. So roughly speaking, this essential skeleton really it's kind of quite very close to a manifold. Yeah. So more precisely, it follows from the minimal model program that first each maximal cone of this cone complex sigma has dimension the same as our Calabi-Yau. And the second, each codimension cone of sigma is the base of exactly two maximal cones. So maybe I can draw some. And you can draw some. You have
They're there on the board.
Yeah. So it just means that every codimension cone is the base of exactly two maximal cones, like this. Well, maybe since we are working with cones, we just this. Yeah. So we don't have other pieces attached. Really, kind of like topological manifold around this codimension one. And then each one stratum of the essential divisor is a smooth rational curve. So one stratum of the essential divisor corresponds to this codimension one cones. It's a smooth rational curve containing exactly 2 zero strata. And finally, the zero locus of the volume form is disjoint from the one strata of the essential divisor. So this gives, as I said, the geometric picture is that this dual intersection cone complex is quite close to a topological manifold outside the codimension 2. Yeah. So this is our this is the dual complex that we were looking at, the dual complex given by the essential divisor, which is homomorphic to the essential skeleton. And we can also consider the dual complex, the bigger dual complex, the dual complex of the whole divisor D. Yeah, so if we consider the big dual complex of the whole divisor D, Berkovich constructed a strong deformation retraction from the analytic space U analytic to this dual complex for YB. Because this construction doesn't have, this construction, it depends only on the complexification, right? It doesn't see the volume form or the essential divisor, and this deformation retraction is only about the dual intersection complex for YB. And inside we have this smaller part spanned by the essential divisors, but it just sits inside. For the moment, we don't have any retraction directly to the essential skeleton. We want a retraction to the essential skeleton because that's what the SYB conjecture predicts. But for the moment, in this setting, for the Berkovich retraction, it only goes to this bigger non-essential skeleton. But that's okay. We currently work with that. And let me just remark that since you use it in Y, the complexification, all this dual cone complex for the skeletons, it also has a natural complexification. So the deformation retraction extends to the bigger space. Yeah, this is the basic diagram. Yeah. Let me just give a remark. So here maybe you see it's a little bit unsatisfactory because from the SYB conjecture in mirror symmetry, you really want SYB vibration over the essential. Okay, so we get extra pieces here. So one way to get a vibration over the essential skeleton is that we use the minimal model. A minimal model means that all the divisors are essential. So once we use minimal model, then the essential part and the non-essential part, they are just the essential part and the bigger part, they are just equal. So then the Berkovich deformation retraction produces us the SYB vibration we want. And we studied this in my paper with Johannes and Chen Yang, where we use the minimal DLT model to get this non-Archimedean SYB vibration using this Berkovich retraction, and we prove that it is an affine torus vibration outside the codimension 2, which is exactly what was predicted by Konasevich and Soboman for this non-Archimedean SYB vibration. Yeah, but here for this talk, I will not use our theorem. I will just work with this one, this diagram above. Yeah, so here we will only use the rejection half, which is only an approximation of the non-Archimedean SYZ vibration. We will not use this thing in my paper with Johannes and Chen Yang for the following reasons. First of all, it's just nice to be able to work with all complexification, not just the minimal complexification, because we want this flexibility to be able to change between different complexifications. We want to make blow-up and blow-downs for the complexifications, and we want to study how the mirror behaves under this change of complexification. So we don't always want minimum. And furthermore, in the minimal model, we know that minimal model usually have singularities. So that's why it's called minimal DLT model instead of minimal SMC model, which do not exist in general. And these singularities cause trouble when we do enumerative geometry. Okay. Are there any questions so far? Yeah, so that's the basic setup for this non-Archimedean SYZ vibration. So here, let me give an example. Yeah, so here is an example of Calabi-Yau surface. And in this case, the essential skeleton is homomorphic to R2. And we have this non-Archimedean SYZ vibration from the analytic space identification of U analytic to the essential skeleton. So we can show that outside the zero, all the fibers are, it's really trivial affine torus vibration. Affine is just the word in non-Archimedean geometry. So essentially, trivial affine torus vibration just means that it's locally the same as the one given by the valuation, coordinate-wise valuation map for the identification of the algebraic torus. Okay. Yeah, and above zero, we have some singularities. So next, we will consider the moduli space of holomorphic disks like this, analytic disk, with boundary on some torus fiber. Yeah, now let me describe. So now I will explain how this disk gives rise to something this tropical, something piecewise linear on the essential skeleton. Okay. Yeah. So let's consider C a quasi-smooth K-analytic curve of genus 0. Quasi-smooth just means smooth, but possibly with some boundary. So we denote the boundary by this boundary C, and also we have some marked points. So you boundary plus usual code. Oh yeah. Boundary has a meaning here. In Kate formalism, boundary doesn't make sense because that boundary point is not a point in Kate formalism. Therefore, in Kate formalism, there is no boundary point because he didn't take into account enough points. And the great observation of biology is that when we add enough points, we just get a much nicer topological space, and we see much more geometrically. So there, the boundary has a meaning which is related to the topological boundary, but not always. I think boundary is always contained in the topological. There is some statement in that book. Oh, but it's easy to know what is the boundary. It's just for any point. Yeah, the definition boundary. It's not a curve. Boundary of the analytic space. So for any analytic space X, and we have a point small x, and we say that this point is an interior point if we can find a small, if we can find an open disk or polydisk containing the small x and containing the bigger x. In this case, x is called an interior point. And points that are not interior points are called boundary. That's the definition. Yeah, and okay. Okay, so we have a boundary, that's it. And we also have some marked points. So although the analytic space is something in general very hard to visualize, but for curves it's very easy. The underlying topological space for curves is just homomorphic to an infinite tree. So yeah, like this infinite tree. This black point is the boundary of the curve here, and we also have some marked points. P1, P2. That's all. This is what an analytic curve looks like. Since it's a tree, we can consider convex hull of all the special points, the boundary and the marked point. And if we get a finite tree now, we call it the skeleton. It's called the skeleton. There's also a way to see this skeleton in terms of this volume form as above, but here in the case of curves, it's just much easier. Take a convex hull. Okay. And now, if we have an analytic map from our analytic curve to the analytic space Y, let's say we have an analytic map such that it hits only the essential dividers of Y, and it meets the essential dividers only at these marked points Pi. We use Pi to keep track of where the curve hits the boundary. So we have this F from C to Y, and we have the Berkovich retraction to the skeleton, not essential yet. And the essential skeleton sits in this bigger non-essential skeleton. Yeah. So what we really want is some tree in the essential skeleton. What we really want is this blue arrow. We want a map from the skeleton of the curve to the skeleton of the log Calabi-Yau variety. Yeah. So in general, it's just not possible. I mean, what we want is to get something like this picture. We have I can use this mouse. So we have this analytic disk, and it map. So we want to get something piecewise linear in the essential skeleton, like here. That's what we want. So as I explained, this analytic disk is an infinite tree, and inside we already have a skeleton of the disk, and we just want the skeleton to map into the skeleton of the log Calabi-Yau into this like this plane. But at this moment, all we have is this map F. The skeleton sits inside C, and this Y retracts to the skeleton YD, and inside we have this essential skeleton. And we want a blue arrow here, but in general, we don't have. When I worked with Sean Keel, he really wanted to have this blue arrow, and then we developed a notion of skeleton curves. And of course, so using some quite detailed study of how the volume form interacts with the moduli space of curves, we do have a special notion of skeletal curves for which this blue arrow actually exists. And when the blue arrow exists, this blue arrow represents, in some sense, the partialization of this of the analytic curve. But here we will not use it. It's something very nice, but then it's kind of like what I did with Johannes and Chen Yang, with minimal model, things become nicer. And also here, it's nice with skeletal curves, but we want to do things more generally because this will, if we can do it more generally, it's just more flexible for later, for many later problems. So here we will not use skeletal curves. We will just define the associated span by the composition. So in general, this blue arrow, it just doesn't factor. And we will simply define the span to be this composition, like the skeleton of curve sits in the curve, then it goes to y and then maps to the skeleton of yd. And it will not go into, in general, it may not go into the essential skeleton, but that's okay. Yeah. Okay. So motivated by the SYD mirror construction, we are interested in counting analytic curves with spans in the essential skeleton. And our goal is given a piecewise integral affine map from H from a nodal metric tree to the essential skeleton, we want to study the moduli space of maps from some curves with boundary to y, whose associated span is the given combinatorial, this piecewise linear map. This is our goal. So we are given some combinatorial data, this tropical piecewise linear map, and we want to study the moduli space of maps from analytical curves with boundary to y with the given span. Okay, so now let's consider some trivial examples. Yeah, so we take U to be the two-dimensional algebraic torus, and we take torus simplification of U, just P1 times P1. In this case, every divisor is essential. So the divisor is just this for rational curves. The skeleton is just R2, and essential skeleton the same here, and it compactifies, it extends to infinity. So the extended one is this compactification minus infinity plus infinity expression. It's just this is our skeleton R2. And then we consider a span, which is simply we map the interval 0 infinity to this R2. So we take embedding in the x coordinate and put a 0 for the y coordinate. So we just consider this. I can use a different color. Okay, and we are interested in the moduli space of holomorphic disks, which project to this way. So what does it look like? Yeah. So the question is, what's the moduli space of identity curves mapping to this identity space, y, with this given y, which like projects to this space. Okay, so we see that it's the same as the maps from a holomorphic disk and closed unit disk D to disk times the circle S. So by circle, I mean simply I have disk D, and this is the circle. Circle simply given by the disk is given by the inequality action value of coordinate less than or equal to 1, and the circle is just given by the equality equal to 1. Yeah. So the moduli space and the codes that we are interested in are exactly maps from disk to disk times the circle, and which is an automorphism on the first vector. Yeah, since it's automorphism on the first vector, and anyway we will be quotienting by automorphisms, therefore the moduli space just becomes the same as maps from a disk. Here I should remove this one, D1, that is one dimensional. The same as maps from disk to the circle. And now we can write it just by power series. Maps from disk to circle is given by function on the disk, which we can write as sum, as an infinite, as a power series, sum of AI xi, where AI lives in some field extension because we are considering moduli space. So we have all kinds of field extensions, and also the norm of AI goes to 0 when I goes to infinity. And furthermore, we ask the norm of A0 to be 1 and the norm of all AI to be less than 1 for all, should be for all I greater than 0. Yeah. So the moduli space is just very simple, given by this power series. So we see that it's a bit problematic because we have all the coefficients of a power series. So this moduli space is infinite dimensional because we can change all the coefficients. Okay. Let's consider a related example. Now we consider maps from unit disk to unit disk. I mean, the previous example we considered is really trivial because somehow everything just like in this direction it's isomorphism, and in that direction everything just gets contracted. And now let's consider some example where things are not contracted. So we consider maps from disk to disk, sending the circle to the circle. And again, we can classify these maps in terms of power series. So these maps, they are given by functions. Again, these maps are given by a function on the disk. And the functions, all the functions on the disk is lies in this K angle bracket X, which means which is called the Tate algebra. It's just a power series with the condition that the coefficient goes to 0. The coefficient converges to 0. That's the definition of the Tate algebra. And here, all such maps are given by special elements in the Tate algebra, such that one coefficient has norm 1, exactly one coefficient has norm 1, and all the other coefficients have norm less than 1. Yeah, so that I, for which the norm of AI is equal to 1, we call it the degree of this map phi. Okay. And now we consider MD, let MD be the space of such maps of given degree. Oh, sorry, I wrote it twice. Yeah. So again, we see that it's again undesirable because this MD is infinite dimensional. It's just we can change all the coefficients while keeping the condition about their norms. And the second, we can also continuously interpolate between different MD because you just move like one coefficient to make its norm bigger and bigger, and then it reaches 1 and move other coefficients smaller. So all the MD, they are kind of connected. That's not what we want. We want them to be kind of separate by the degrees. Yeah. And let's just recall that this phenomena is completely different from complex analytic geometry. Because in complex analytic geometry, if we consider maps from disk to disk, keeping the circle, then it's a finite dimensional moduli space. And it follows from the Schwartz lamp. So by in complex geometry, all such maps from disk with boundary to itself is given by this formula, so-called finite flush product. It's simply given by some complex number of norm 1, and then it's a product like this, where AI are the zeros of this map. Mi are the multiplicities of zeros. Yeah, so in complex geometry, it's nice finite dimension, but in non-Archimedean geometry, it's just bad. Okay. So now let's go back to non-Archimedean geometry. What we want, what's really bad is that we just have too many coefficients in non-Archimedean geometry, and they cause us all the trouble. So what we want is to get rid of all the higher order coefficients. AI, as soon as this I is greater than the degree, and in this way we can separate all the moduli space with different degrees. Yeah. So the observation is that this phi, the observation is that this map phi can actually be made into a polynomial of degree d if we ask the following extension property. So if it's equal to a polynomial of degree d if and only if we can extend it to a map from P1 to P1. So we just extend d to P1 and extend phi to phi tilde such that the opposite closed unit disk. I have this d here, and now it's extended to P1, and we have the opposite disk d prime, and we ask the opposite closed unit disk to hit infinity at only 1 point. So the phi tilde inverse of infinity is just infinity. It's kind of a very simple observation, but using this extension property, we get rid of all the bad coefficients that cause us all the trouble in non-Archimedean geometry. Yeah. So this suggests us a general strategy for obtaining a well-behaved moduli space for non-Archimedean analytic disks by a similar extension property. And let me explain this extension property, which we call some boundary regularity condition. Okay. Yeah. So in order to illustrate this boundary regularity condition for For this purpose, now we just consider maps from from holomorphic disks. Our theory also works for maps from curves with more boundary points, but just to simplify the thought, let's just consider only a single boundary point. So closed unit disks. Let's consider maps from closed unit disks to spatial space. And as we have seen in the above examples, the moduli space of such maps with a given span is just a span. It's infinite dimensional and it seems poorly behaved. Okay, so the rough idea is that for the purpose of instance of corrections in SYZ mirror symmetry, the boundary circle S, this boundary circle S, it actually lies in a pretty nice place. The boundary circle S lies in the place of the amplification of U, where we have this trivial affine torus vibration. Remember that SYZ conjecture says that when we have for the SYZ vibration outside the codimension 2, it's just the locally trivial torus vibration. So, and when we do the instance of corrections, the boundaries goes to the place where we have this torus vibration. So here, it's just locally isomorphic to this trivial torus vibration from the amplification of the algebraic torus to Rn. And so then this picture is not so different from these trivial examples we were talking about. If we just look where the boundary goes. And we have this boundary circle going to this place with this trivial affine torus vibration. And we just want this map to be as simple as possible. We have this map S to this algebraic torus to be as simple as possible. So now the idea is very simple. We just why don't we just ask it to be like boundary of some like trivial of some very simple map. So yeah, so that's what we will do. So motivated by the above examples, we propose the following boundary regularity condition. We have this circle S mapping into this algebraic torus, and we just ask that S extend like before. So before we have this D, and we ask it to extend to this complement D prime. Now this D might map to something more complicated. This is our D, and this is the circle S. And again, since this S lies in this in this simple space, we just ask that this circle equipped with the opposite orientation again extend to a closed unit disk D prime. And then the map from the circle to the algebraic torus just extend to a map from the opposite disk D prime to some toric complexification of this torus, such that the opposite map D prime hits the toric boundary only at 0.
So you know the problem with
here the tendencies we have. I mean, when I say it hits boundary at 0, it may have tendency. Yes, but just the kind of that's all. And this toric complexification is nothing to worry about because it's just a way to do it to extend it, to have a place so that the infinity can go down. Okay. And yeah, so the idea is really that the circle goes to this simple place, and then we just put the simplest condition for the circle. And everything looks like just a toric geometry. Yeah, and this idea is actually a variant of what I have been discussing with Maxime for a long time, where we don't consider this toric variety, we consider something smaller, but it turned out this toric variety is just much easier to work with. Yeah. So geometrically, it means that, yeah, so now maybe you have some worry because for our curve, we have this part. This is the part which maps to this part of the curve, it maps to our original y. And this maps to this GM. And then this part maps to the toric variety. So somehow you see that this toric variety has nothing to do with this original Calabi-Yau. It's just two completely different spaces. Although they do have some small intersection, which is a small domain inside this algebraic torus. But essentially, this toric variety and this Calabi-Yau, they really have nothing to do with each other. Yes.
Yes, that's one thing is possible, but I just want to make sure I understand this right. So classically, we work over complex number, and we work over complex. The thing you count is this part which has probably been used before.
Yes.
And then you want to replace it by extending the app cap.
Yeah, but this cap no longer lives in the variety.
Yeah, so so this will go outside.
Go outside.
Original. But it's this idea is like if we look at the one you call S, it has some class in epsilon.
Yeah.
This class epsilon is
The X still lives inside the variety.
yes, just inside and then this like the degree of this S in G.
The degree of S is like the, yeah, we can also see the degree of this.
Yeah.
How the other side gets the boundary.
Yeah.
Thank you for the question. So here, really,
So can you say one more time how you decided what factorization of this GM to take?
it doesn't matter. I said that it's the computation is only needed to have a place where this point can go.
The moduli space will.
Yeah, the moduli space doesn't depend on the complex computation. Yes. Yeah. So yeah, but here the main trick or the main idea is that we are really letting this tail to go outside of the variety. I don't think it's easy to do it in complex analytic geometry, but in non-Archimedean geometry, as I said, this circle really goes to this standard place, and then we just impose the condition for the map from the circle to this standard place. But the trouble is that this standard GM and this YN, they really have nothing to do with each other, except that on the small domain, they coincide. So geometrically, it means that we are gluing the toric variety Tn to Yn along this very small domain. They coincide. they have nothing to do with each other except this small domain. And we just glue them together. And this small domain, we have some freedom to choose because we can always choose it even smaller. Let's just choose it to be a so-called closed polyhedral affinoid domain. It's just that affinoid is analogous to affine. So affinoid is next, and we want it to be closed. And the polyhedral is also next in non-Archimedean geometry because it's related to something, the algebra being finite type. Okay. Yeah, and most importantly, we want that over that domain, we have trivial affinoid torus vibration. So that's the key property we want for this domain. And this domain here, I denoted, I drew it by this gray shape. So we have this this part, this oval part, which is y-analytic, and we have this this piece, gray bigger piece. It's the analytic. It's the toric variety. They coincide at this gray part where we have affinoid torus vibration. We just glue them along this gray part. Okay. Yeah. So once we glue them, we see that now the modular space of analytic disks from D to the log Calabi-Yau by analytic with given span and satisfying the boundary regularity condition is now equivalent to the modular space of rational curves from rational curves, this rational curve, which is the gluing of a disk D with the opposite disk D prime along the circle S to the glued target space V, which is the gluing of Y and T along this gray domain G, such that we ask that I already drew here. We ask this D to map to Y, and we ask the D prime to map to the auxiliary toric variety, reaching the infinity only at one point. And this is the picture. Yeah, so we have, we used to just have this red disk inside the log Calabi-Yau we started with. And now we have the extension of the boundary to this orange disk, but the orange disk lives in a completely different space in this toric variety. And by considering this gluing, we reduce the modular space of analytic disks to the modular space of rational curves into this glued target satisfying these conditions. So
the toric variety is the same for all the given spine.
Any toric variety we can take, it doesn't really matter. As Yang already pointed out, the modular space is independent, doesn't change. Yeah. Okay. Yeah. So we have this glued curve. We denote the glued curve. Oh, sorry, I should put the primes here. Yeah, so the glued curve is glued from D and D prime. We just denoted by B and E. Just to change letters. So B means body and E means end, because in general, we may have a body. So this is just where we have one boundary. But assume later we may work with more boundary points. Like this, and we will be, so this will be the body. It might not be a disk anymore, it can be a pair of ends, and then we have this end. So that's why we change the notation from D to body and end. Yes.
Can you also allow genus with a B?
Oh, for the genus, yeah, why not? We can, it works too with genus. It's just yeah, for most of the things we did for the modular space, we can allow higher genus. That's a great observation. Later, when we really count things for higher genus, then for the virtual dimension, maybe one has to be a bit more careful. Yeah. Before I end my talk, maybe I just say this. Okay. Before I end this morning talk. So we have a worry is that this new type of space Z as a doubling of the log Calabi-Yau with the torus variety is not projected. And it's not even proper, not even separated. It's just a very really terrible space. Because usually the total reduce is like that. So how is it possible to obtain a reasonable modular space of curves in this strange fluid space? And this is what I will explain in my afternoon talk. So in the next part of the talk, we will establish several properties of the modular space of curves in this strange fluid space V. And these properties are essential for the non-Archimedean SYV incidental corrections. So I will talk about 4 properties in the afternoon. Namely, boundarylessness means that it has no boundary. Compactness and properness and smoothness. So this is the plan for the afternoon. Okay. And all these properties require some different sort of techniques, which I will also introduce in the afternoon. Thank you very much for your attention.
Good. Thanks, Tony, again.